make comment, conclusion. Yeah. Conclusion for this 2.4 example. Yeah. So the conclusion, because the limit calculation we work, it's the continuous version, continuous variable version, not discrete variable version. Yeah. But at the end, we need to go back to the discrete variable version. Yeah. Here the question is, because the limit we calculate, so that is the continuous variable version. We know the continuous version and the discrete version, these two versions, slightly different. Yeah. The meaning slightly different. Yeah. For the continuous version, we agree, after we apply the L'Hopital's rule, we agree the limit is 0. Yeah. But the question, how can you go from limit 0 for the continuous version to the limit 0 for the discrete version, right? So that step, yeah, because you need to, make a jump, okay? Yeah. There is a small gap between these two versions. Yeah. How do you bridge the gap, right? Yeah. So here I want to explain that little gap part. Yeah. How do we bridge that little gap? Yeah. Here we need to use the definition of the limit. Yeah. So we need to recall the definition of limit. Limit concept. All right, yeah, all right. Here, I do not need to copy the definition of limit, okay? I don't need, yeah. So here I just use the, idea, the basic idea here. Yeah. Now, let's look at this continuous version. Yeah. Here, when x goes to infinity, and x, we know it is a continuous variable. Yeah. And here, some detailed information we didn't mention. How does x go to infinity, right? Because when you make x approach to infinity, there are many different ways to approach to infinity, right? But which specific way we use to make x approach to infinity? That's my question. Yeah, because there are millions of different ways for x to approach to infinity. Okay? All right. So here, let me give you some example. Yeah, so many different ways. Yeah, one way. Now, I take x value. Yeah, because when we make x approach to infinity, basically we take a sequence of values for x. Yeah, not just the one value, a sequence of values for x. Okay. Yeah. When we take the sequence, can we take the sequence as 1 square, 2 square, 3 square, n square? We use this way, we can approach to infinity, right? Is this way a legal way for x to approach to infinity? Right? We can also take root of 1, root of 2, root of 3, root of m. This way also we can go to infinity, right? So the sequence. Yeah. And log, yeah, let me use a natural log, okay? Yeah. So we do not need to specify the base number. Log ln of 1, natural log of 2, natural log of 3, sorry, natural log of n also approach it to the infinity, right? Yeah. So which way? Because in our discussion, we never mention which way we take for x to infinity. Yeah. Then, so here, by the definition of the limit, anyway is okay. Okay? Yeah. Any of these ways, yeah, you know, and you can have other ways. Yeah. If the sequence approaches to infinity, then it's legal. Okay? Any sequence that approaches infinity is legal. We can use for x value to be taken here in the limit. Okay? All right. Now, the last step, we take one special sequence for x to approach to 0. That's the positive, consecutive positive integer. 1, 2, 3, 4. And this particular sequence, this sequence corresponds to the discrete variable, right? Yeah, it's legal. We just take this special sequence for x. And by the definition of the limit, it approaches infinity. Yeah, the limit is infinity. And that limit, that's the discrete version of the limit. Yeah. Yeah. So that's the argument, you know, we can use to bridge the gap between continuous variable version and a discrete variable version. Yeah. So that's my, you know, comments for the last step. Yeah. The goal here, you may ask me why you spend so much time, you know, talking about this kind of details. Yeah. The reason is simple. We want to make rigorous logical reasoning, right? We don't want to leave any hole in our logical reasoning because there is a possible hole there. Okay? Yeah. So here we want to fix that hole. Yeah. Another thing is, if some of you read the textbook, then the textbook uses this discrete version directly. It does not use the continuous version. It takes the derivative on this discrete version function directly. Yeah. So that's not rigorous. Okay? That is not rigorous. Yeah. Just let you know. Yeah. So when you read, so you need to be aware of the, you know, that kind of problem. Yeah. All right. Yeah. So let me move to the next question. 2.5. Oh, yeah. My remote control, yeah, I disconnected. Yeah. All right. 2.5. Show that power function n to the d some constant for a constant, yeah, let me say positive constant. Yeah, positive constant. Yeah, yeah. All right. This power function belongs to little of exponential function with base a to the n, but the base number should be greater than 1. Yeah. Yeah. The D here in this question, D greater or equal to 1. Yeah. But later we can make this D any positive number. Okay? Yeah. Even less than 1, still correct. Yeah. Yeah. Less than 1, even more correct, right? Because the power function will be smaller. Yeah. Yeah. You compare a smaller function with the very big exponential function. So you get a little O. Yeah. All right. So now let me show you how to apply. Yeah. So here now definition, because little o we take a limit, right? Yeah. Little o case, very easy. Yeah. We have no choice. We can only use the limit way. Yeah. All right. So we just calculate the limit. Yeah. All right. When we calculate the limit, yeah. So here, let's look at our D number. D number, here I give you D greater or equal to 1, but I didn't say D is an integer, right? D may not be an integer. D could be any real number greater or equal to 1. Yeah. So you can think about if D is not an integer. Okay? For example, D is root 2. If D equals root 2, okay, root 2. Any technical problem, right? When you work on exponent number, some non-integer exponent number, any problem? Yeah. So here, we need to, when we write our solution, proof here, problem solving here, we're doing problem solving, right? Yeah. So here I want to recall the problem solving strategies we have learned so far. Yeah. So we can apply some appropriate problem solving strategy. All right. Let me mention one of the strategies we used before. Yeah. So that is, when we work on our data, so here, our data, our data here, we may have many cases, right? So here, in particular, the cases about D number, exponent D number cases. D could be integers and non-integers, different cases. Yeah. So when we work on our data with different cases, we learned one strategy before. It tells us we should always start with the simplest case, right? Simplest case. Yeah. Here, let's apply that strategy. Yeah. Here, the integer case simpler, right? Yeah. Integer case simpler. Yeah. So Ernest join us. Yeah. Here at this time. Yeah. All right. Integer is the simplest case. How about we work on the integer case first? So we make our assumption. We assume, so in our first step, we assume that D is a positive integer, some positive integer. Okay? Yeah. D greater or equal to 1, and we only consider the integer case at the beginning, because later we will move to other cases. Yeah. But the first case, integer case. All right. If we assume d is a positive integer number, then when we calculate this limit, here we use the continuous version. Okay, so we switch to continuous version quickly. Yeah, we have that experience. Yeah, so we do not need to, do a lot of preparation. Yeah, let's just calculate continuous version directly. The nice thing about integer number at the exponent position, when we take derivatives, much easier, right? Yeah. Yeah. If for non-integer version, we can still take derivative, but not as good as the integer case, right? Yeah. Could be very messy, right? Yeah. Non-integer, could be messy. Yeah. Integer, no problem. Technically, we feel comfortable. Yeah. For integer d, yeah. All right. First, now we plan to apply L'Hopital's rule. So we check the indeterminate form condition. Yeah. So no problem. Yeah. It's an infinity over infinity indeterminate form. So now we can apply the L'Hopital's rule. Yeah. All right. Then we take derivative. Yeah. Numerator is a power function. Power function, we have the formula for the derivative of the power function, right? Yeah. D times x to the d minus 1, power function. Right. Then derivative of the exponential function, yeah, so we have this formula. Natural log of a times original exponential function, a to the x. Yeah. All right. So after the first step, yeah, next, what should we do next? Here there is a question about this exponent number, d minus 1. D minus 1. Okay, yeah. If d greater than 1, then if d greater than 1, it is still an infinity over infinity indeterminate form. Okay? That means we need to apply L'Hopital's rule another time. Okay? Yeah. Yeah. So let's consider that case. Yeah. So d greater, because for the general d, yeah, so most of the time d is greater than 1. So we should take the derivative another time. Yeah. All right, the second time, yeah. Still, we apply the power rule, yeah. D times d minus 1, then times x to the d minus 2. Yeah. Denominator, so we just need another natural log of a factor. Yeah. One more natural log of a factor. Yeah. All right. So then, this time, the exponent becomes d minus 2. Yeah. So if d is greater than 2, it is still an indeterminate form. That means you need to take another round. L'Hopital's rule. Another round. Yeah. And keep going until your whole form is not an indeterminate form. Okay? Until the numerator, yeah, specifically, the numerator is not, does not go to infinity anymore. Right? Then you stop. Okay? The numerator does not go to infinity when x goes to infinity anymore. Then you can stop. Otherwise, you need to keep doing this. Okay? Keep doing this. Fortunately, at some point, we can stop. Okay? Yeah, so this process can terminate at some appropriate point. So what's that point? The point is when the exponent number becomes d minus d, that is 0, x to the 0, it is 1. 1 is a constant. Yeah. It never changes when x goes to infinity. that means the numerator is not indeterminate, right? The numerator is determinate. It's a constant number, determinate. Okay, that's the end of your L'Hopital's rule. Okay, end of your L'Hopital's rule application. Okay, all right. So this is the last step. Okay, so the numerator is d factorial, denominator natural log of a, this number to the dth power, then times a to the x. Okay, all right. After simplification, yeah, you look at this limit. Denominator goes to infinity. Yeah. Numerator is a constant number. So the whole fraction, the limit of the whole fraction is 0. That's the answer. That is the answer. Okay? Yeah. So here you can see you need to apply L'Hopital's rule d times. D times. D, some integer, some positive integer. That number of times. Then you can stop and find the answer. Okay? Yeah. Yeah. So, and this step, it is for the simplest case. Yeah. The positive integer, simplest case, but not general case, right? It is not a general case. Yeah. So for the general case, you need to cover the general case. Yeah. So you only, yeah, although you get an important case, yeah, but the remaining more general case, you need to show it is correct. Yeah. Now let's go to the general non-integer case for d. Yeah. This time we can work on non-integer case for d. All right. Yeah. When we work on the non-integer number d, because we have the experience of the integer case. Yeah. So that is our partial result. Yeah, let's say that is our partial result. So we can do the proof on top of that partial result. So now we are in a much better situation because we can use this partial result. Okay, yeah, yeah. All right, so the question, how to use the partial result? Yeah. Now let me show you how to use the partial result. Yeah. Question, yeah. When d is a non-integer, yeah, we know, yeah, because there is one problem. If we apply the L'Hopital's rule, we can never stop, right? Yeah, think about, yeah, because at your exponent, every time because you minus some integer, yeah, you can never make the exponent of that power function to be 0. Then you can never stop. So that's something pretty bad, right? Yeah. Although so you can get around it. Yeah. So definitely you can get around it. Yeah. All right. So here we want to make some bridge, yeah, or stepstone. Yeah, sometimes people also call a stepstone. We need to, yeah, because there is a gap. Yeah, how do we bridge the gap? We need to find some appropriate stepstone to help us, cross that bridge, yeah, cross that river. Okay, yeah, things like that. Right. Yeah, so now let me do a special treatment. Yeah, all right. Your d, here we assume it's a non-integer number. Okay, non-integer number. All right, yeah. Then, can we use some integer number to approximate? Yeah. We know it is not integer, but we have partial result for integer case. Now we want to connect this d to an appropriate integer number. Then we can apply our integer result to get something useful. That's the idea. Okay? Yeah. To do that, let us approximate this d by a reasonable integer above this d, higher, larger than this d. Yeah. You know, a nice candidate. That is the seeding function of d. How about that? Because if we take seeding function of d, that first, that's an integer. Second, it's greater than, strictly greater than d. Okay? The seeding function of d, it's an integer, so we can apply integer result. How about that? Our integer result. Okay? Yeah. All right, so let's do it. Integer result. Okay? All right. Let us write limit, x to the infinity. Yeah, sorry. Yeah. All right. X to the d. All right. So let me just, save one copy. Okay. Yeah. So the original form, I do not need to copy. Okay. I save one copy step. Okay. Now I write the decomposition step. I want to decompose the original fraction into, remember the bridge form. Here, what we are doing? Doing the bridge way, the bridge form. All right? All right. That is x to the d over x to the d seeding function. How about that? Okay? The denominator, we intentionally put a power function x to the ceiling of d. Then we have to make it up. Yeah, we cannot put there free, right? So here we have to put x to the ceiling of d in the numerator, then a to the x. How about that? Okay, this is decomposition. This time we have two fractions. How about that? Two fractions. Okay, all right. Then this is a nice bridge. So we are very close to our final answer. Nice bridge. Okay, all right. Yeah. All right. The first fraction, yeah, d less than, so here, do you agree our numerator is less than the denominator? Denominator larger because exponent larger, right? Yeah. X is a very large number. X is a very large number, okay? The exponent of the denominator is higher than the exponent of the numerator. So can we say the first fraction is less than 1? Because denominator is larger. Okay? Larger. Yeah. Then the second fraction, because ceiling of d it's an integer, can we apply our partial result? We just did before. This limit goes to 0, right? Yeah, the limit of the second fraction, yeah, we just prove it. That's our partial result. We can apply it. And we replace that limit by 0. So 1 times 0, it's 0, right? The whole thing is 0. The whole thing is 0. Okay? Yeah. Then That's our final result. Yeah. So even for non-integer d, we make that bridge, we can get the same limit 0 result. Yeah. Then we go back, discrete, from continuous version to discrete version as before. Yeah. So we prove it. Yeah. Yeah. So here I use this example. I want to show you some effective problem-solving strategy. Okay. So what's that strategy? Yeah. Let me summarize the problem-solving things we learn, or we applied here. Okay, all right. First, we start from the simplest case. We always work on the simplest case. Okay, yeah. After that, then from the simplest case, then we move to the general case. Yeah, general case, but there is a gap. So definitely, there is some gap. So we need to bridge the gap. Yeah. How to bridge the gap? Yeah. So usually we find some appropriate stepstone to establish some bridge between these two cases. Okay, yeah. Yeah, so here, yeah, you need to, because here the critical step, the key to the success, critical step, you need to be able to discover this fraction decomposition form. Yeah. Okay, yeah. If you can see this kind of decomposition, yeah. So people commonly used decomposition like this. Yeah. Then, so you can solve the problem. Okay, yeah. All right, so we complete this 2.5. Yeah. Yeah. We have two more examples. Yeah. So let me continue. Yeah. And these last 2 or 3 examples are closely related to our first homework assignment, the current big assignment I just gave you yesterday. Yeah. Closely related to that. Yeah. So let me, after I finish these 2 examples, let me make some comments related to homework assignment number 1. Yeah. All right, so let's go to the 2.6. All right. Yeah. Log base 2 of n belongs to little of root of n. Yeah. All right. Yeah. So another similar question, but just different functions. Yeah. Here, let's just do the similar calculation. Yeah. Work on the continuous version, and we know it is infinity over infinity indeterminate form. So we can take L'Hopital's rule. Yeah. Then we take derivative. Yeah. We apply the derivative formulas. Yeah. All right. Yeah. So the denominator function, we write it as a power function. Yeah. But this time, the exponent is 1/2. Yeah. Positive number. Yeah. Less than 1, but positive number. Okay. All right. Now, derivative. All right. Denominator, we can still apply the power rule, right? So that r, yeah. So remember that the formula x to the power rule, r times x to the r minus 1. Okay? This here, r equals 1/2. Yeah. 1/2. So we have, this formula. Numerator, still the formula, so 1 over bracket natural log of 2 times x. After simplification. Now, before we go to we need to simplify it before we go to the next step. Yeah. After simplification, you can see it is not an indeterminate form, because numerator is 2, a fixed number. So we cannot apply L'Hopital's rule another round. So we have to stop at this round. Then the good thing is the denominator, there is a variable part, x to the 1/2. So root of x. It goes to infinity. It goes to infinity, denominator, so the whole fraction goes to 0. So the limit is 0. Okay? Then we can get back to discrete version. So we prove it. All right. But this is a special. So here the question. This is a special functions. So we want to go to a little more general. So our last example in this module, part C, the last example in part C, it's a more general version. So we go from special case to a general case. So 2.7, this time, log, so log, because here actually the base is not that important. So here we use the natural log, natural base, natural log base. Then the power function, our g function, the power function, that d, it's a general d. Okay? This time it is a general d. We only require that d is positive. No more. Okay? D is greater than 0. That's all we need. Then we want to show natural log of n belongs to little o of this power function n to the d. All right. So let's calculate the limit. All right. Infinity over infinity. So we check it. Pass the checking. So we can apply the L'Hopital's rule. All right. Derivative of natural log, it's 1 over x. Very simple. So that's the reason we want to use natural log here, because its derivative is so simple. Then, derivative of the denominator, apply the power rule. D times d to the d minus, x to the d minus 1, power rule. All right, then simplification. After simplification, we have 1 over d times x to the d. It is not in determinate form anymore. So we cannot consider L'Hopital's rule. So we have to stop. And we can find its limit immediately, because denominator goes to infinity. When the exponent d is a positive number, then x to d must go to the infinity. Okay? No matter how small d is, d could be a small number, because x goes to infinity, so x to the d also goes to infinity. So 1 over infinity, the limit is 0. Then we go back to the discrete version, so we complete the proof. All right. So here you can see example 2.7 is more general than example 2.6, because example 6 here the exponent of this root m function, it's 1/2. Now we change that 1/2 to a general positive D number. Yeah. So more general. Yeah. So any D, any positive D, we have this result. All right. Then, next, I want to make some comments related to our homework assignment. Yeah. In our homework assignment, we have a few questions related to these two examples. One 2.5, another 2.7. These two examples. Yeah. So you can apply the results of these two numbers, two examples directly. Okay? Yeah, directly. All right. Then when you apply, so here, let's look at the first case. The first case is this, n to the d belongs to little of a to the n. Yeah. So we know a greater than 1. Yeah. All right. D, yeah. So D, great, positive. It's okay. Yeah. Positive. Yeah. All right. Here you can see regarding this exponent D number, we do not say how large is that D, right? We do not say how large is that D. That means if D is a constant, if D is some constant, no matter how large it is, it's always true, right? Yeah. Yeah. Because we rigorously, we proved this result. Now we believe. Now we're 100% sure it is correct. We're 100% sure it is correct. Okay? Yeah. So now we apply this result without hesitation. Okay? So we just apply it. Okay? All right. So now, let me show you the way I apply it. Okay, all right. And to the, because you do not limit that D number, right? Yeah, nobody puts any limit on this D number. So I can choose some extremely large D. How about that? Okay, 1 billion here. Okay, although I can put more zeros, but just give you the idea. It's enough. Okay? So I raise this n variable to 1 billionth power. So you can imagine how large is this function. Okay? You can imagine how large is this function. Okay? Super large. Yeah. Remember, our n goes to infinity. Our n goes to infinity. Then n already could be some huge number. Then we raise to 1 billionth power. You can imagine how large it is, right? Yeah. All right, so now we do comparison. This side, A, the only limitation on A, it is greater than 1, right? How much greater? Nobody says any specific information about that A. It only needs to be greater than 1. That's enough. Okay? Yeah, so then I have the freedom to choose any A number that is greater than 1. Okay? All right? Yeah. So now I choose 1.00. I put many zeros as I like, right? Yeah. That's the A I choose. Only a tiny bit more than 1. Okay? Yeah. Very close to 1, but still A is strictly greater than 1. Okay? All right. Then we raise this number to nth power. Okay, nth power. Because we want to match this exponential function, a to the n. Match that exponential function. Then, after I write out these two expressions, then I ask you to compare these two functions. Which one is eventually larger than the other one when n is very, very large? Okay? That question. Which one, has larger value when n is very, very large? When n goes to infinity, okay? There is no limit on n. Okay? That is the question you need to answer in this homework assignment. Okay? Although the number I use slightly different from the numbers here, but the meaning is similar. Meaning is similar, okay? So here the problem is because many students, if you use your intuition here, probably, so you mean, because our intuition, many times it may not be reliable, right? Our intuition could be wrong. Our intuition could be wrong, okay? This is the special case that, for some of the students, your intuition could be wrong. Okay? So here, I just give you this much information. Okay? You need to think about it. All right, that's the first one. I have a few minutes, so I want to talk about the second case. Second case, we need to connect to this example 2.7. All right. 2.7, we compare another two functions. The first function, natural log of n. Second function, a power function, n to the d. So this power function, the only restriction on d is this d is positive number. That's all we need. All right? So now I have freedom to choose that d. Okay? All right. So n to the d. So this time I only need to choose a d number that is barely greater than 0. Then I make the condition satisfied. Okay? All right. So now I choose 0.00. I put many zeros. Okay? That should be enough. So you get idea. Okay? 1/millionth. Okay? The exponent number 1/millionth. All that can make it 1/billionth, but not necessary, right? You just get the idea. Okay? So 1/millionth. So you can see here the exponent number extremely small. Extremely small. Now I ask you to compare these two functions and which one would eventually beat the other one on their values. We compared their values. Which one would eventually be larger than the other one? Okay? So here, the similar situation as the first case, because if you base on your intuition, it may not be correct. It may not be correct. So here I'm talking about intuition here. Because it is not easy to describe the intuition here, right? Different people may have different intuitions, right? But here I like to use some some example I saw before. Yeah. So one student in this class, in some previous semesters, yeah, you know, probably last year, yeah, as I remember, the last summer, yeah. Yeah, it's not important. Yeah. So one student asked me one question. Yeah. So here I'm talking about something related to this intuition. Yeah. But that student, in order to, you know, get some understanding, comparing, you know, the functions I gave you here. Yeah. So here, in order to compare, you know, so that student used some online graphic calculators, try to draw graphs, online graphic calculators, yeah. But the result is not good, yeah. Because the expression we have here, the huge expressions, right? You know, if you want to draw graphs of functions as big as we have here, you know, you get trouble quickly, out of range, yeah, because we know the display area of your graph calculator, it is limited, right? Quite limited, you know, yeah. So you run out of your space, okay? So you cannot see, you know, the long future behavior, right? Yeah. When n is extremely large, how can you see that? Okay? Yeah. Yeah. So the result wouldn't be very good. Yeah. So that's the, you know, problem. So that student, yeah, show me, you know, graphs, you know. Don't try it. Don't even try it. Okay? Yeah. 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 Because the function too big. Yeah. Too big. Okay? Yeah. Yeah. You know, run away to the universe. Okay? You know, these two big functions, you know, quickly run away into the far universe. Right? Yeah. So we couldn't imagine. Yeah. But here, trust our results here. Okay? So when you answer those questions in this homework assignment, trust these two results, because we did rigorous math proof. Just trust it. Okay? Yeah. All right? So you apply the results. Yeah. Yeah. Even if our results are against your intuition, you need to trust it. Okay? Yeah. So that's my comments related to, you know, current homework assignment. Yeah. All right. Then, yeah, last 2 minutes, I want to say something about this homework assignment, because the deadline is here. Yeah. Here, you know, and help you to prepare for this big assignment, very important, big assignment. The deadline is July the 12th, okay, Sunday. All right, yeah. So you have this weekend you can work. Yeah. So this weekend, yeah. So I hope you can work as much as you can this weekend, yeah, because the deadline is next weekend. So you have 2 weekends before the deadline, yeah. But why working this? Do not delay too much, okay, into the next week. So the reason it is very important, so you try to work very hard in this weekend, because after you work in this weekend, you may have many questions, right? Because this assignment is very challenging. Here, I'll let you know. This whole assignment, Yeah, some of the questions, yeah, not all questions. Some of the questions very challenging. Yeah. After you work, so definitely you will have. Oh, yeah, I run out of time. I will finish in 2 minutes. Yeah. Definitely you will have many questions. Yeah. Then next week, remember we will have 2 lectures next week. Then in those 2 lectures, you can ask me any questions in this assignment. Yeah. Because then I can give you hints. Okay? So then you have chance. You can ask me. So I will, I will try to answer. Definitely, I cannot give you the answers, but I can give you helpful information. Helpful information to help you solve those challenging questions. Okay? Yeah. So in that way, you won't waste 2 lectures in next week. Okay? Because after those 2 lectures, so then it may not be that easy to ask me questions. Although still you can ask. Yeah. But may not be, reach me easily, right? So you can ask me using those 2 lectures. Yeah. So then I will find a way to give you hint information. Hint. Okay? So I plan to make videos to give you hint information. Because I cannot use our precious class time to do the hints. Yeah. We need to cover the lectures. Yeah. But after you give me the questions, then I make videos. Then I post the videos. You just study the videos. All right? Okay, yeah, so that's all I want to say. Yeah, so try your best to work this weekend. Okay? Then let me know your questions next week. Yeah. All right, that's it.